Hello chemists, welcome to Lecture 1 and Matter and Chemistry. Let's first discuss chemistry and matter. Chemistry is the study of the composition and changes of matter. By matter, I mean anything that has mass and volume. What I mean by mass is the amount of physical material or particles that something usually has. By volume, I mean the amount of three-dimensional space that something occupies. So anything that has a certain amount of physical material and takes up a certain amount of 3D space is known as matter. Examples of matter include desks in the classroom, soda that you drink, steam, which is a gaseous form of water, and salt water. Next, let's discuss matter's composition. Matter is made up of particles, specifically atoms, molecules, and on occasion ions. Atoms, first off, are the smallest, simplest units of matter, and they are singular in nature. For example, here we have many atoms of the element iron represented by the chemical symbol Fe. Notice here that each atom of iron is represented by a single brown sphere here. So each of these single brown spheres represents the smallest, simplest unit of the element iron. And each of these is singular in nature. Next, we have molecules, which is a little more complex. Molecules have two or more atoms chemically combined together in some way. You should note for molecules, as you see kind of in this diagram from just the colors, that molecules can consist of only one type of atom chemically combined together, or they can consist of two or more different types of atoms chemically combined together. For example, in the case of molecules of oxygen or O2, notice how each molecule here of oxygen consists of two atoms of the same type, oxygen, bonded together to make a molecule of oxygen. So that's an example of two or more atoms of the same type chemically combined together. On the other hand, with water or H2O, notice here that you have two different types of atoms combined chemically together to make up water. Specifically, if you look at each molecule of water here represented by each unit, you'll see that you have one atom of oxygen, O, shown by this gray sphere here, bonded to two atoms of hydrogen in red here. So here you have two different types of atoms, hydrogen and oxygen, chemically combined together to make a molecule of water. Specifically, in each unit, one atom of oxygen shown by this gray sphere bonded to two atoms of hydrogen shown in red here. Okay? Now let's discuss matter's four types of properties: extensive, intensive, physical, and chemical. Extensive properties depend only on the amount of substance or how much you have. Examples include mass, volume, and length. Let's take the example of water filling up a glass jar. The more water you have in the jar, the greater the mass, since there's more molecules of water. The more volume the water occupies, since there's more water obviously there occupying 3D space, and the higher the level or length of water. Alright, now intensive properties, on the other hand, depend only on the substance's identity, not on the amount, only on the identity. Examples include temperature. For example, if you cut a block of gold into pieces, it'll be the same temperature. It doesn't matter that the amount has changed once you cut it. It will still stay at the same temperature. Color is another example. Sulfur is yellow, while table salt or sodium chloride is white, due to their different identities. Density is another example. If you put ethanol, which is in rubbing alcohol, into water, ethanol will float, since ethanol's density is less than that of water's. This difference in density is due to ethanol's identity being different from that of water. Reactivity is another example. Certain metals are more reactive than others are in water, due to different identities. Solubility is another example. Oil is not soluble in water, while sodium chloride is, due to different identities. And melting and boiling point. Sodium chloride or table salt has a higher boiling point and melting point than sucrose or table sugar does, due to their differences in bonding, as you'll learn later. Now, how all of these properties depend only on identity. To drive this point home further, let's say you have 5 grams of sucrose or table sugar versus 100 grams of sucrose. If you have these different samples with different masses, it doesn't matter that their masses are different. Since you have the same substance with the same identity, sucrose in both cases, both samples will have the same melting and boiling point, since these temperatures are intensive properties that depend only on identity. Because intensive properties depend only on identity, we can use them to identify substances, meaning we could look, for example, at a clear liquid boiling at 100 degrees Celsius and atmospheric pressure and say, it's water, based on its intensive characteristic property of boiling point.
because water is the only substance that will boil at 1 degree Celsius at 1 atm or atmospheric pressure. All right, specifically, these intensive properties will change if the substance's identity changes somehow.
Next are physical and chemical properties. Physical properties are properties you measure or observe without changing composition. So when you measure or observe these properties, you only change the substance's shape, size, or arrangement, but not its composition and not what it's made out of. All right, examples include color. You can see sulfur's yellow color without changing its composition, melting point, boiling point, and state of matter. So when you find the temperature ice or a solid water melts at, you only change its arrangement and distance between particles in changing state from solid to liquid during melting, but you don't change the fact that you still have water. Similarly, with boiling point, when you find the temperature water boils at, you change its arrangement and distance between particles when you change state from liquid to gas. However, you do not change the fact that you have water even when you form steam, which is water in a gaseous state. Another example is conductivity. Copper conducting electricity doesn't change the fact that you have copper even if you pass electricity through it. Density is another example. You can measure the density of a metal block without changing its identity. And finally, solubility. Solubility means the ability to dissolve one substance in another. For example, if you dissolve table salt in water, you only physically combine and mix the particles around, hence rearranging how particles in sodium chloride will orient to the water molecules. But you don't change the fact that you have sodium chloride and water physically combined. They make no new substance at all. All they're doing is physically mixing around, but they're not forming anything new. So the properties of salt and water are retained or kept here. Specifically, salt water is still wet from water and bitter due to salt. Note here also that intensive and extensive properties usually fall under the umbrella of being physical properties. All right. Next, we have chemical properties, which relate to a substance's ability to interact with other substances and form new substances. Alright, since new substances form when measuring or observing chemical properties, composition will change as a result of chemical properties. Examples include the ability to burn. The element magnesium, for example, would burn by reacting with the element oxygen in the air to form a new integrated substance known as magnesium oxide compound. Another example is an ability to rust. The element iron and oxygen react to form a new compound, iron oxide, with a thin reddish layer. So they're forming a new compound there. You started with two elements, iron and oxygen, and you're forming a compound at the end that's completely new substance, iron oxide. And finally, the ability to react two substances to form a new one. For example here, the metal element sodium and the non-metal element chlorine gas will react to form sodium chloride or table salt in solid form. In all these cases, what you should notice is composition has changed due to completely new substances being formed. Also note that if a substance changes completely, then the chemical properties will also change, and this is due to the substance's identity itself changing. For example, going back to sodium and chlorine reacting to form sodium chloride, you start with sodium and chlorine separately as elements, then you end up with sodium chloride at the end. So the element sodium metal in solid form is very reactive with water, while the element chlorine gas is very toxic. When you react these two together, they form a completely new substance, the compound sodium chloride in solid form, which is very stable and safe for consumption. Why? Well, the difference in properties between sodium chloride stability at the end and the individual properties of the elements you started with is due to the fact that the substance's identity has changed. Basically, if you have a different substance, you'll have different chemical properties, including the ability to react. The last thing you should know here is there's a relationship between the structure of atoms and properties. Specifically, differences in the composition of atoms, either in number or in type of atoms, or in the structure of atoms, meaning how the atoms are arranged, will lead to different physical and chemical properties. All right? For example, look at oxygen molecules in the air, O2, versus ozone molecules in the troposphere, O3. Oxygen molecules, or O2, differs from O3 in the sense that O2 has one less oxygen atom than O3 does. Even though O2 and O3 have the same element, oxygen, the difference in their composition arising from different number of oxygen atoms in each molecule will lead to differences in physical properties like boiling point. And this also has consequences, by the way, for breathing. Ozone, or O3, would be dangerous to breathe in as it can damage your lungs, while oxygen is relatively safe in comparison. Next, let's discuss two types of changes in chemistry, physical and chemical. Before we start, no equations for these changes shown like this will involve symbols for substances or mixtures, such as H2S here on both sides. All right. You'll also see parentheses in these equations to indicate states of matter, S, L, G, and AQ, which we'll discuss in a minute. And also make sure you note that matter before and after each change will be separated by an arrow in the middle to imply that some kind of change has occurred. Next, particle diagrams shown like this one will always show particle arrangement, particle types, the bonding within each particle, as well as the movement of particles. First, we have physical changes, which are changes that alter a substance's particle arrangement, but not its composition. Examples include phase changes like melting and evaporation. So with melting, when you melt an ice cube, for example, to form liquid water, you don't change the fact that you have water. The particles are just rearranged in space further apart in changing from a solid to a liquid. Evaporation, the particles again are just spaced further apart in changing liquid water to form steam. Dissolving is yet another example of physical change. If you dissolve sodium chloride in water, you simply rearrange the particles physically, but you do not make a new substance. Finally, ripping. If you rip paper, you still have paper, it's just that the particles are rearranged. Next, physical change equations, which look like this or like this, show the same substance on both sides, just different phases in parentheses. So S is for solid, L is for liquid, G is for gas, and AQ is aqueous, meaning a substance dissolves completely in water. For example, as shown on the left here, H2SG or dihydrogen sulfide gas will dissolve in water during this change that's physical to form H2SAQ or dihydrogen sulfide solution. So you have H2S on both sides, just one is gaseous phase and the other one is aqueous phase. All right, you see a similar situation for I2 solid or iodine solid becoming iodine gas at room temperature.
Next, a physical change particle diagram, which looks like this or like this, shows particles rearranging without changing composition. So the particles don't detach or attach to form a new particle type. They just simply space out or move around. For example, as shown here on the left here, H2S gas and water are separate before the physical change of dissolving, and they only move around during dissolving. There's no attachment or detachment of particles. The particles are simply just moving around. A similar situation occurs with I2 solid transitioning to form I2 gas during this change of sublimation. Or if you add heat to I2 solid at room temperature, the particles are just spaced further apart and changing from solid to gas, such that after the change, the I2 gas particles will be spaced further apart in the corners of the particle diagram box here, here, and here. All right, next we have chemical changes, which form different substances with different chemical properties. So these changes will alter the substance's identity or composition. Examples include burning, rusting, which is reacting with oxygen, corroding, which we'll learn about later, reacting two substances to form new substance, and electrolysis. Electrolysis, by the way, and please write this in your notes, is the passing of electricity through a liquid or a solution to decompose or break down a more complex species into simpler ones. We'll see more on this in a minute. Now, chemical change equation shows different substances being produced with different chemical properties since their identities change. For example, with the electrolysis of water, as you'll see down here, electricity will be passed through the compound liquid water here to decompose or break it down to simpler substances, specifically as shown in this chemical change equation, 2 units of the element hydrogen as a molecule and 1 unit of the element oxygen as a molecule. All right, so the compound liquid water before the chemical change forms 2 new substances, the elements hydrogen and oxygen, after electrolysis, meaning the chemical properties after this chemical change are different due to new substances with new identities being formed. Finally, the particle diagram for a chemical equation or chemical change will show breaking or forming of either new molecules or atoms. For example, in the particle diagram for water's electrolysis, 2 water molecules, each with 2 atoms of hydrogen in red bonded to 1 atom of oxygen in gray, will break apart and bond in new configurations to form new molecules. Specifically, 1 molecule of oxygen shown by 2 gray atoms of oxygen bonded, and 2 molecules of hydrogen shown by 2 red hydrogen atoms bonded together in each hydrogen molecule. All right.
Last, let's discuss 3 main states of matter: solid, liquid, and gas. First, we have solids, which have a definite shape and a definite volume. By definite, I mean that they have their own shape and own volume when in a container. So for example, if you put magnesium solid or MgS metal into a container, it would have its own shape and volume. It would just sit there and not try to mold to the container. It would just sit there exactly as it was put in. All right, so solid particle diagrams show the particles touching and forming a definite geometric pattern of some sort. I don't know what this shape is, but it's a definite geometric pattern of some sort. So notice that the particles are touching and they form a definite geometric pattern of some sort. That's because solids have very strong attractive forces, hence why they're very close together, because of their strong attraction. On the other hand, liquids, the second state of matter, have an indefinite shape but a definite volume. What that means is they have their own volume depending on how much of the liquid you have, but they do take the shape of their containers. For example, if you put liquid mercury into a container, it would have a specific volume depending on how much you have. However, the liquid mercury would take the shape of its container, no matter what. All right, so if you have a cylindrical cup, then liquid mercury would take the cylindrical cup shape like this. All right. Now, note here that liquid particle diagrams show particles spaced further apart than in solids. The particles are close somewhat in liquids, but they're not touching because they're spaced further apart. And they have a somewhat irregular pattern due to liquids having a rather indefinite shape. Finally, we have gases, which have an indefinite shape and an indefinite volume. So what that means is they take the shape and volume of their containers. All right, for example, xenon gas, if placed in a sealed room, would fill the whole volume of the room and take its shape. All right? Finally, gas particle diagrams show particles spaced very far apart, basically with the particles touching the corners of the particle diagram box like this. Notice how these are touching the corners, right? With a very irregular pattern and filling of the space of their container, even compared to liquids. That's because gases have very weak attractive forces compared to these other two phases. Now, if you notice, based on these diagrams, solids have the most ordered state of matter and the strongest attractive forces. Liquids have less order and less attractive forces. And gases have the least order and the weakest attractive forces of the three phases. All right, that's it for today. See you tomorrow. Bye-bye.